Okay, let's continue our discussion. So, let's solve the example 3.9 together. Okay. Oh, sorry. Yeah, 3.9 together. So basically, as you can see, the water flow through a pipe reducer as shown in figure 3.9. So here is the static pressure 1 and 2 measured by manometer, okay, containing oil. So basically this one is oil, okay. So the specific gravity is less than 1. Okay, to determine the manometer reading H. So here the H, what is the H? We need to determine. So first, to solve this problem, we need to use the Bernoulli equation, right? So here is our strategy. So first, we are going to use Bernoulli equation. Okay. The second, we need to also use the continuity equation because it has a different diameter, right? And third, as you notice that this problem used the manometer, so we need to calculate the pressure difference by using this relation. Okay, this is our strategy. Okay, so first we need to use the Bernoulli equation. So let's make an assumption. Assumption first, inviscid, and second, incompressible, and third, it should be within a streamline, and also the steady. So streamline in the point 1 and 2. Okay, this is our assumption. So because of this assumption, we can successfully use the Bernoulli equation, right? Bernoulli equation here should be this one, right? And the second, for the continuity equation, so Q1 should be identical with the Q2. So which means that A1 V1 equal A2 V2, right? And here A1 represent is because this is circle, right? And this one is circle and the diameter is given. So we can written as like this, right? So combining is equation 1 and equation 2. Equation 1 and 2. We can summarize our equation like P1 minus P2 equal gamma Z2 minus Z1 plus rho V1, V2 square 1 minus A2 A1 square, right? And also we need to use the manometer concept here to determine the pressure, right? So here, as you notice that the P1, P2 has a different height and also there's some manometer, right? So for the manometer, P1 over here minus gamma Z2 minus Z1. So this one represent this pressure, right? And minus gamma L, so this one, right? And minus gamma H, so this one, right? Equal P, sorry, we should also represent this one and this one. this one is SG gamma H, right? Plus gamma L equal P2, right? This is the, we can determine by using the manometer concept, right? So if we summarize this equation, we can written as P1 minus P2 equal gamma Z2 minus Z1 plus 1 minus SG gamma H, okay? And also, if we combine this equation and this equation, so let's call this is equation 3 and this is 4, equations 3 and 4, we can written as 1 minus SG gamma H equal rho V2 square 1 minus D2 D1 square, right? So this is what we got. So if you rearrange this equation, you will get the H. So this will be answer for this question. Okay. So, and also, and this is the plus alpha concept, the cavitation effect in confined flows. So if flow is coming from here to here, you can draw the streamline, right? But the thing is, because of the too much pressure difference, in that case, the pressure difference can also be considerable for flow of the gas. This may introduce compressibility effects, okay? But the thing is, for the liquid, this may result in cavitation. So cavitation is this kind of the bubble. Okay, so basically this is air, not the liquid. But even though we put the liquid, but because of the pressure is too low, so this because of this air, I mean some air dissolve in this water, I mean this liquid, so that this will be evaporated like this. So it generates this kind of the bubble, okay? So it will be bubble, this kind of things we call the cavitation, okay? So when you see this diagram, at the first over here, the pressure is the absolute pressure, okay? But if the flow pass through this narrow channel, in that case, in the very slow flow rate, which means that the V is very slow, in that case, we can successfully use the Bernoulli equation, because it did not happen the cavitation effect. But the thing is, if the flow is very large, in that case, this should be diagram looks like this. But the thing is, below the certain point, the vapor pressure, this air is pops up, so it no longer going down, and then it's steady at this PV value. So at this point, we call the cavitation is occurred. So this is you should also consider, if you design this kind of narrow channel in the liquid, the cavitation effect is also very important. Okay. So another application of the Bernoulli equation is the flow measurement. Okay. So there is a if we put this kind of the channel, so this channel we call the restriction. So this one we call the orifice, and this kind of the thing we call the nozzle, and with this kind of the thing we call the venturi. Okay. So if you measure the pressure difference 1 and 2, in that case, we can successfully obtain the flow rate. Flow rate mean is the Q. So if we apply this point 1 and point 2, because it is same streamline, we assume that this is in the same streamline, so we can make this kind of the Bernoulli equation, right? So because there is no height difference, so this term will be neglected, so you can written as pressure drop, differential pressure as a function of the different velocity, right? And also this one at the 1 and 2, it has a different diameter, which means it's a different area. So we can also use the continuity equation as well. So continuity equation, we can also obtain the velocity as a function of the geometrical parameter as a A1 and a flow rate. So if you combine 1 and 2, in that case, you can successfully obtain flow rate as a function of the pressure drop. So which means that if you measure the pressure drop over here, and also if you know the geometry, in that case we can determine the flow rate, right? Okay, so this is the very general concept of the flow rate and the pressure drop relation. So flow rate is, generally speaking, it is proportional to the differential pressure 0.5 to the 0.5, okay, the square root of the differential pressure. Okay, so this is the general concept of the flow measurement. Okay, so based on our learning, so we are going to solve the problem 3.11. Okay, so please stop the video and think about yourself, and then let's solve this problem together. Okay, so here because this chapter is we only know learn the Bernoulli equation, so definitely we should use the Bernoulli equation, right? So to use the Bernoulli equation, there is an assumption. The first assumption is inviscid and steady and incompressible, and this is in the streamline. Streamline. Okay. So, okay. If we use this concept in that case, we can written as Q equal. Let me see. Q equal A2 P1 minus P2 rho 1 minus A2 minus A1 square. Okay, this is what we derived in the previous page, right? So because we know this relation, so here we can tell that P1 minus P2 equal Q square rho 1 minus A2 A1 square to A2 square. Okay, from this equation you can restate we can make this kind of the equation. So the thing is here, the density is not given, only the specific gravity is given. So the density we can calculate using the specific gravity like this. Okay, so here 0.85 times 1000, so 850 kilogram cubic meter. So this is our density, and third, A2, A1. It should be diameter difference, right? So 0.0601 square will be 0.36. Okay. So because we know that this one and this one, so now and also we know that this one, so we can put the order value in the case we can determine the pressure drop. So P1 minus P2 equal, and Q is given here and here, right? So first we are going to use this flow rate, okay? Because we need to determine the range, right? So 0.005 second, putting all the value over in this equation, 850, 1 minus 0.36 square, and 0.06 square, and what? And this one should be square, right? Okay, so if you calculate this one, this result will be 1160 Pascal. Okay, and likewise for the delta P with the largest Q. The largest Q is the 0.05. So if you put all the value over here again, in the case this value will be 116000 Pascal. Okay, 116 kilopascal. Okay, so this one 1.16 Pascal, kilopascal. Okay, so our answer will be 1.16 kilopascal to 116 kilopascal. So this will be our answer for this example. Okay, this example is quite easy. So another application of the Bernoulli equation is a flow measurement in the this kind of the gate. Okay, so in this gate, as you can see, the area is a little bit different. Okay, so in that case, we should use the contraction coefficient concept as well. Okay, so if you analyze point 1 and point 2 to connecting the streamline, in the case we also made the assumption inviscid, incompressible, and steady. In the case, you can use the Bernoulli equation like this, and here the 1 and 2 is open to the air, so it should be a pressure should be identical as a atmosphere, right? So in that case, this P1, P2 will be neglected, right? And this term you can written as like this because the gamma is rho g, right? So this one rho g, so density will be neglected. So you can return, we can make this kind of equation. And also here we can also use the continuity equation because it has a different diameter, so we can get another information over here. So A1 V1 equal A2 V2. So here the A1, so this one, the area is the gate width times this height, right? And for the A2, also gate width times the Z2, so this height, right? So if you plug in this relationship into the Bernoulli equation result, in the case you can get this result. So, and here also, as you notice that Z1 and Z2, the z1 is much larger than z2, so you can summarize the result like this. Okay. So usually for the contraction coefficient, like here the a over here and z1, this is if the less than 0.2, the contraction coefficient is usually 0.61. Okay, so this result, the flow diagram looks like this. Okay, so here is another example to solve the gate. Okay, dam problem. Okay, so let's solve this example together. So please stop the video and think about this problem by yourself, and then come back to this problem and let's solve this example together. Okay. So since we derived this equation, so Q equal, let me see, Q equal Z2B minus G2Z1 square, right? And here, let me see, the Z1 over here is the 5 meter, right? And Z2, we don't know that, right? And we know the A is a 0.8, right? So A divided by Z1 is a 0.8 divided by 5 is the what? 0.16. So this is the less than 0.2. So we know the contraction coefficient. So CC value will be 0.61, right? So CC value over here, we can written as Z2 divided by A, right? Z2 divided by A. So here we can calculate G2 as A times CC. So here A is the what? 0.8, CC is 0.61. So G2 will be what? 0.488 meter. Okay, so now we know the G2 value. Okay, so I will erase this part. Okay, so so here, as you notice that we know the Z2 and B is given as 6 meter. This will be B. This one equal Z1. This one equal A. This one equals Z2. So G2 is a 0. meter, right? So here we need to calculate the approximate the flow rate per unit width. So which means that Q divided by B. What is this? Okay. So Q divided by B is, we can written as Z2 2G Z1 minus Z2 1 minus Z2 Z1 square, right? So we know the order value over here. So let's just put the order value over here. Okay, so Z2 is a 0.488, 9.81. Z1 minus Z2 is 5 minus 844, right? And divided by 5 square. So this answer will be 4.61 meter square per sec. So this is the flow rate per unit width. Okay. So, and also to the discussion, we can also use this equation, right? If the Z1 is much larger than G2. So here G1 is 5 and G2 is 0.488, right? So here the equation is Q equal to 2B 2GZ1, right? So Q divided by B will be 0.488 times 2 times 9.81 and 5. Okay, so the result will be 4.83 meters squared per sec. Okay, so this result is quite similar. Okay, so if this difference is much large, this result will be much more similar. Okay. So let's review the Bernoulli equation. The Bernoulli equation is the P plus log V squared divided by 2 plus gamma Z equal constant along the streamline. So be careful. Again, to use the Bernoulli equation, the flow should be steady and inviscid and incompressible, right? And also this guy we call the elevation head. So this one represent the potential energy, and this one we call the pressure head. This one represent the flow energy or the pressure energy, and this guy represent the velocity head. So this one represent the kinetic energy. Okay. So hydraulic grade line and energy grade line is very similar concept. So, but the thing is, the hydraulic grade line consider the pressure head and elevation head. Okay, is some summation of the pressure head and elevation head, but the energy you should also consider the kinetic energy as well. Okay, so this one represent the flow energy, this one represent the potential energy. So these two concepts is a little bit different, but the reason why we differentiate these two is that we need to differentiate the kinetic energy. Okay, so energy grade line usually is the constant. Okay, because this value should be constant along the streamline. If we made the assumption like this, steady, inviscid, incompressible, so this value should always constant. So if the flow from the left to the right, in that case the energy should be always the constant along the x direction. But the hydraulic grade line, if we neglect the kinetic energy, so this kinetic energy converted as a potential energy or the flow energy, right? So this will be changed. So this kinetic energy will be slightly decreases as the flow coming from the left to the right. So these two concepts is try to tell you that the energy grade line is always the constant, but the hydraulic grade line, it can be changed along the streamline. Okay, and also there is another example to understand, to see the schematic for the hydraulic grade line and the energy line. Okay, so hydraulic grade line is this guy, and energy line is this one. So as you notice that for the energy line, this is always the constant along the from 1, 2, 3. But the hydraulic gradient line at this orifice or nozzle, because the area is decreases, so the velocity of the V1 compared to V1, V2, the V2 is much large. It changes as the what? Kinetic energy, right? So this kinetic energy, if you so the kinetic energy, sorry, and hydraulic gradient line, again, this one represent the potential energy plus the here the potential energy plus the flow energy. Okay, so and also likewise this one is also represent this one. Okay, and also this one is also very similar. The energy line is always constant, but the hydraulic gradient line is changed because of this nozzle, and the other part it is represent the it is does not change the hydraulic gradient line because the potential energy and flow energy is interchangeable within this kind of the flow. So again, to use this concept, we should make an assumption: inviscid, incompressible, and steady. Okay, this is our assumption to use energy line to make a assumption that the energy line is always constant. So, but some textbook claim that, as you can see, the energy gradient line is in the left hand side is always the constant, right? But here, energy gradient line keep decreasing. So which one is correct? So actually, both of them correct, but the only difference is that in the left hand side case, the assumption is inviscid and incompressible and steady. But here, this inviscid concept here is a viscid concept. Okay, so it is considered the viscosity effect as well. So if viscosity effects are important, so which means that not the inviscid flow. So this one, viscid flow. Okay, the viscous effect are important. The total head does not remain constant. Here, total head represent the what? Energy gradient line. So due to loss in energy as the fluid flow along its streamline, this means that the energy line EGL is no longer horizontal. So which means the constant. Okay. So in the actual case, the energy gradient line also keep decreasing because of the viscous effect. So again, what is the viscosity? So viscosity is related to friction, right? So it is very same concept in the dynamic. So this ball at this ground, there is a ball. If you drop the ball at this point, in the case, at this point, the flow energy, the kinetic energy and the potential energy at the 1 and 2 should be identical, right? This is the free fall situation. But the thing is, if there is a loss of the friction because of the wind or the air, so in that case, this energy is not conservative. it will be not constant because of the friction. So this is the same concept. If the friction is very important, so which means the viscosity effect is very important, in that case your energy grade line is keep decreasing. Okay, and also if we supply the energy by using pump and also extract the energy by using turbine, in that case the energy grade line, the hydraulic grade line also suddenly changed. So this is also very very common, right? So restriction of the Bernoulli equation should be steady, frictionless flow, which means the inviscid flow, and the no shaft work, so which means that there's no external energy like pump or turbine, and also the flow is the incompressible flow and there is no heat transfer rate, and we assume the flow along a streamline. If this condition is satisfied, you can use the Bernoulli equation. So usually this one is the plus alpha concept, right? No heat transfer rate. So heat transfer rate also is very important because energy also related to the temperature, right? So, but in the fluid dynamics, we do not consider the effect of the temperature. So, this one is the plus alpha concept for our lecture, okay? And except these two concepts, the no sharp work, no heat transfer rate, these four conditions, you should always check before solve the example in a fluid dynamics lecture. This is another extra item. So if your flow within the irrotational region, so irrotational mean is that at the near the boundary, the flow will be rotated because of the rotation energy. So this kind of the concept in the fluid mechanics we quantify with the vorticity concept. So vorticity we can quantify using the curve v vector. So if you do not understand, you can, for now, you can just ignore this concept, okay? So vorticity, we can calculate the this z here vw uvw represent, this is x velocity, this is y velocity, and this is z velocity, okay? So here z velocity related to the y. If you use this concept, in that case you can calculate the vorticity, and for the two-dimensional, which means there is no z, in that case we can vorticity written as like this, okay? So for the irrotational flow means that the fluid particle does not rotate it, okay? Fluid particles are not rotating, but fluid particle is rotating. In that case we call the rotational flow. So for the irrotational flow, this value should be 0, okay? So irrotational flow should be, this force should be 0, okay? So usually for now, you can just know the concept over here. The near the boundary layer, near the surface area, the fluid particle is usually rotated. But over the boundary layer, so far from the boundary layer, fluid particle will not rotate it, okay? So in this yellow region, we call the irrotational flow region. So, very special case. If you make an assumption, the flow is the irrotational. Okay, so we make the another assumption. The flow is the irrotational. In the case, in the case, your Bernoulli equation, you don't need a streamline concept anymore. This value will be always constant if flow within the irrotational region. Okay, so this is very special case. But for your most of your example, is the pipe flow, right? In the pipe flow, the fluid particle is very close to the wall, so this will be not irrotational. This flow will be rotational flow. So you cannot use this concept, but if you solve the external flow, in the case, we can use the you can make an assumption like a irrotational flow, and then you can apply the Bernoulli equation in anywhere. So this is the extra item. And okay, so unsteady compressive flow, yeah, also the Bernoulli equation for the unsteady compressive flow, the result is looks like this. Okay, this one is we already discussed in the previous lecture, right? And if the unsteady and incompressible flow, you can use this equation. Okay, so again, so this is just the extra item. Okay, let's solve the equation not equation, example 3.18 together. Okay. Okay, please stop the video, and then if you're ready to solve this example, then let's come back and then let's solve this example together. Okay. So consider uniform flow in the channel. So uniform flow channel as shown in 3.18. The liquid in the vertical piezometer tube is stationary. Discuss the use of the Bernoulli equation. Point 1, 2, 3, 4, 5. Okay. At the near this point, it assumes that the fluid particle is spin. So this one is the rotation. So if we made an assumption like a inviscid, incompressible, and what steady, the point 1 and 2, we can use the Bernoulli equation, right? Because it in the same streamline. And also point 3 to 4, also we can use the Bernoulli equation as well, right? And but here you should also know that the Bernoulli equation, the point what, this 1 and 2 and 3, 4, it will be the across the streamline concept, right? Streamline concept. And here, as you know, because the streamline are straight and horizontal, the between equation the 3 and 4, we can also connect it. Okay. So if you recall the previous page, I mean the previous lecture, this concept. Okay, so this is the across the streamline concept, the constant across the streamline, right? And because dn plus gamma z equal constant, right? So here r is infinity because this is straight line. So p plus gamma z should be constant in the p1 z1 and the p3 gamma z3, right? So we know this result, and also here the flow is uniform, so we also know P1 equal P3. So which means that P1 plus we can also use the Bernoulli equation along the 1 and 3 as well, right? So which means that 1, 2, 3, 4 is all connected. So all connected means you can use the Bernoulli equation in anywhere 1, 2, 3, 4, because 1 and 3 we use the across the streamline concept, and 1, 2 it is same because of the within the streamline, and also 3, 4 it is also constant because it is also within the streamline. Okay. And here another one, you should also know that P4 and P5 it is fluid particle is rotated, right? So we because of this we cannot use the 5 and 4 is not the same. So to be specific, P4 equal P5 plus gamma H, right? So this result represent that point 4 and 5 you are going to get the wrong result if you apply the Bernoulli equation. So here the answer will be, you can use the Bernoulli equation point 1, 2, 3, 4, and you cannot use the 4 and 5. So this will be the answer for this example. Okay, so this is the end of today's lecture. So if you have any question, because this is an online lecture, so feel free to come to my office and then we can discuss together. Thank you.